Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's Christopher Tech. We're delighted to have him, and I shall not waste his time.
Okay, thank you for the short introduction. So this allows me to introduce a little bit myself. So I did my master in Graz and on the topic of so-called technical mathematics, which is a mixture of applied math and computer science. After working a few years in industry, I started a PhD in Graz as well, at the institute which is now more or less managed by Horst Bischoff. Then I was asked to do a post-doctoral stay at UNC-Chapel, where I got in contact with Mark Polyface, and basically at the end of my stay at UNC, so he convinced me to join his new group at ETH Zurich. So this presentation will contain will contain two parts which are apparently not too related, so I have a difficult time to make some sort of a continuous story out of the work what I did, but I will try nevertheless. And sort of the central aspect is 3D modeling, which led to questions about structure and motion problems, and also the investigations into dense modeling, which then further on attracted my interest in convex methods used in computer vision. So the first part is called Beyond the Reprojection Error, and I want to give you quickly some background on a project we had in Graz at the end, essentially, of my PhD time. This project was called Vienna, not necessary you have to know about it. It has or had somewhat similar goals as phototourism, which we didn't know, of course, because when we wrote the proposal, the phototourism paper was not out yet. It had a slightly different focus because the goal was really first to reconstruct a large fraction of the historic center of Vienna in this particular case, which means we didn't want to focus entirely on the touristic landmarks where plenty of tourists take pictures, but also we would like to have for example, the narrow streets between landmarks model as well, where you know or where you can assume that people have to take pictures specifically in order to get enough coverage to do the reconstruction there. The other difference was that the original idea, which we only partially succeeded because we were undermanned, of course, in terms of manpower. So phototourism takes an approach looking at all the images at first and then picking out the good ones to start and then incrementally growing the 3D model. So here the idea is when you allow users to participate in this project and they upload new images when they take some, that you do not recompute the 3D model from scratch again. So some incremental maintenance of the 3D database. This was also some design goal. Especially, so one student I worked with, he did an amazing job in implementing a structured motion pipeline, which was, let's say, in general not too different what phototourism does, with some more or less minor differences or in the detail. The problem we observed is, so although it is very good or does a good job on recovering large parts, in this case from Vienna, so the famous Stephansdom, if you have been in Vienna. So although it did very often a good job, when there are ambiguities in the images, so like repeating patterns or similar facades, which are really not identical, but to a feature matching procedure, they look similar enough. then you generally have some errors. And in the framework we had, it was basically impossible to gracefully recover from those mistakes. The success of photourism and our approach and all the other works in this area led to might lead to the conjecture that structured motion might be solved if you just use the right features, the right robust procedures and so on. And it is not. And exactly these kind of problems we encountered led to the conclusion, so we have to think more about it. So we, of course, discarded all the failure cases because initially we didn't see any value in that. So I have to refer to Noah's Nameless thesis. He clearly shows some very nice examples for failures where a structured motion pipeline has problems. So in this very extreme case, so the Arc de Triomphe in Paris, so the front and the back side, they look visually very similar, and any feature matching procedure would hypothesize that there is some underlying incorrect, so false positive epipolar geometry between those images. And very often those kind of failure cases in the pairwise matching lead into distorted models, as you can see here, where instead of closing the building, it attaches the reconstruction at the wrong spot, and you have some distorted model, and bundle adjustment, for example, cannot recover from that. So some of our own examples. So from Vienna, the Schönbrunn Castle, which is also very famous. So this is a very extreme data set since you have highly repetitive visual elements in the facade. So there are more images than that. This is just a subset of 3, so there are about 50 images or so. And when you run the structured motion pipeline, or in this case my structured motion pipeline, without considering explicitly the problems, then you might end up with a model like this. So this is already very distorted, and this is the result before doing bundle adjustment. And of course, bundle adjustment recovers or the geometry locally, but on the global scale, the model is completely distorted. So what can be done here? So we looked at 2 possibilities, and the first one is dealing with so-called missing correspondences. And the idea here is, so when we look at this pair of images, which is the Opera House in Graz, and those are images of the opposite facades, they have something in common. So this part here is very symmetric to this part. So a feature detector and the matching procedure will tell you, okay, this feature here corresponds to that one here, and so on. So from a matching procedure, there is a good evidence that there is an actual, in this case, epipolar geometry underlying. But of course, using a human observer, you're immediately aware that something is wrong because so this part does not correspond to that one, and this does not correspond to this one. So you have several options now. So the one option, when you stay with a pair of images, then you need something like single view methodology or like Make3D to have some prior on the depth structure, because then you could infer that here and here something fishy is going on. We had no experience with those kind of approaches, so what we did is instead of trying to having some guess on the 3D structure from a single image and use that, we did something that's geometrically well defined. We use a third image. So essentially, when you look at a pair of images and you have feature matches between, so which give you 3D points under the hypothesis of a visual relation. So the more feature matches you have, the more confidence you have that the underlying estimated geometry between the images is correct. When you look at the third image and you from pairwise correspondences you hypothesize a visual relation between the third image and the two other ones, then you can check. Since from this pair of images I have the 3D points, I have an hypothesis how this relates to the other images. So then I can check how many of the 3D points that should be visible, so that fall in the within the viewing frustum of the third image, are actually detected. And if you have lots of undetected features, then there is some evidence that there might be something wrong in the assumption that this really matches with the other images. This, of course, has the assumption about a strong assumption about occlusions. So, so how did you formulate this? I mean, as standard. So you have some observation that's dependent on, let's say, some local evidence and some observation dependent on some more global evidence. You formulate this as a graphical model, and we restricted ourselves to really looking at triplets of images. So the graphical model is a very simple one, where the unknowns are whether in the triplet of the pairwise relations are okay or they are not. So there's a binary decision, and what you observe is, for example, the number of feature matches between a pair of images. So this is some indication that everything is okay. And then you look at the triplet or the missing correspondences, which depends on all of the pairwise relations. So, and this gives you the factor in this little graphical model. You have a very small graphical model with only 3 binary unknowns. So essentially 8 cases to check, and only 4 of them are really plausible or can occur in practice. So solving this graphical model amounts only to going over 4 values for probabilities. Yes.
How does using 3 views help you with the problem you started with, where you had a facade with lots of almost identically repeated textures?
In this case, not.
Okay. Just to make sure that
yeah.
I wasn't missing anything.
No, this.
No, I think I missed something. You motivated this construction by showing us 2 pictures of the opposite facades. So why do you need the third one here? Why?
Because from 2 images, I mean, there might be not detected correspondences between a pair of images, even if they are perfectly related, because you don't know the depth structure. So it could be that the may go back. So when we as a human have of course a very strong understanding what's going on, but for example, that this and this doesn't show any features. This could be implied that what you see here is out of the viewing frustum here. So you need some idea what's the depth of this region or of this region to really have a stable estimate that you should see those features, and when you don't, then something might have gone wrong. So of course we did not only look at 2 images, so in order to make this work, we capture several images. And when we apply the standard structural motion pipeline, because of the visual similarities, so the 2 opposite facades are really merged into one model, which is not the one you want to have. When you apply this technique and then discard some of the pairwise relations, and then and also if you had a strong procedure separating those parts, then instead of merging everything, so you end up with 2 models which correspond to the to the correct result of seeing really different objects. So you are perfectly right. So there are some shortcomings, and so one of the shortcomings is so the inference is very local, and we had to use a very strict procedure not to introduce sort of force visual relations through the backdoor, because this inference procedure is quite conservative because of feature detector repeatability and occlusion and so on. So you have to quite allow that you miss a lot of features. So when the inference step tells you something is going wrong, it is pretty sure that something is going wrong. So you miss quite some false positive, and in order not to run into troubles, so we had to have a very strict procedure separating the parts, in separate models, such that you do not have the same problems, but from other pairwise relations. And so some of the shortcomings led to that I did not stop thinking about this, and the very complementary approach is this one, where the formulation motivation is somewhat different, although it addresses a similar problem. For example, you have a data set where someone walked around a block in a city and took images, and of course what you have similar facades and repeating patterns, so you might end up with incorrect pairwise relation between images as before. Now what we do here is we look at what's usually called the camera graph, so pairwise relations or hypothesized pairwise relations between images induce some graph structure, where in this case, so the little dots, the nodes correspond to images, and you have an edge between the dots if you have hypothesized, in this case, an essential matrix between the images. So when you walk around a block, you would assume that this camera graph is somewhat perfectly circular, which it is mostly, but what you see are sort of some shortcut edges here. Where do they come from? So actually they come from that, for example, this facade is matched to the orthogonal one, so which is not strictly the right one, and this introduces some shortcut, and you see already in some sense the outcome of the procedure I'm going to explain in the next few slides, that everything that's light gray survived this test. So it seems to be okay, the underlying visual relation or the underlying essential, and everything that's black, that's discarded as an false positive. So how does this work? We have now this camera graph. We have lots of paths generally we can follow in this camera graph, and we can check, are those paths in some sense consistent. So if we started at one image, somehow chain together the transformations or the visual or the pairwise relations we encounter to some other image, and we take different routes, do we end up in the same position? So, and this is equivalent to checking whether going around the loop is going to give a consistent loop. So the idea is really very simple. So if we have we start with the camera here, we have pairwise relations estimated. If we chain together all the relations and come back to this camera where we started from, the obvious question to ask is, do we look in the same direction as where we started from? Or are we at the same position? And if this is not the case, or the orientation and position after chaining the transformation is substantially different from where we started, then something looks bad along the edges. So there are several places where to apply this reasoning. For example, when you look at the level of just essential matrices, what you can accumulate are relative rotations. So which means, are you looking, so after chaining all the essentials, are you looking in the same direction as where you started? at this point, not too much can be said about the translations or the position, but it follow subsequent steps. You can add this kind of reasoning as well. So the thing is to come up with some measure for when you chain together the transformations, how much do they deviate from the identity transformation which you want to expect, and for the radial rotations we just pick the remaining angle in the coordinate transformation, and in other cases it is something like, for example, the Frobenius norm, so how much you deviate from the identity matrix. You can look at some real statistics, and from this plot, so this is for rotations, this is for something like rotations, this is for rotations, this is for positions. You see it's a heavy tail or something like a heavy tail distribution. So what we model is, so the deviation on the assumption that every transformation encountered along the loop is good. This is just some exponential distribution where we have only to determine the value of lambda, so which can be easily done. And in the case that the loop is contaminated by a false positive visual relation, not too much can be said, so we picked a very uninformative distribution for that, which is a uniform distribution. Looking at one loop is not sufficient because it only tells you something and the loop looks probably wrong, but you don't know where. But when you look at many loops, and then one particular edge or pairwise relation between images participates in many loops, this allows us to pin down the most probably incorrect edges by setting up a graphical model and doing inference. Where again, the unknowns are binary variables telling you whether the hypothesized pairwise relation looks good or looks contaminated. So this is the decision you want to come up with. You might add sort of unary priors based on your confidence in the feature matches, which we did not use. And there are, of course, the loop factors, which are the observations of how much you deviated from this perfect identity transformation when you walk along a loop. So this you can solve in different ways, and I think on the next slide, yeah, you see already sort of some outcomes. What we have tried here and gave us relatively similar results on the datasets we used is loop BP, the standard LP relaxation, and also branch and bound, which branch and bound would give us the exact result. So these are for this block dataset a few results. So matches or hypothesized visual relations like this, they are discarded by this procedure, and so here this facade is actually so the one you can't see here, so the orthogonal one to that. So a lot of those shortcuts are removed. Yes.
So how many cycles do you add? Because there are infinitely many cycles, right?
I mean, you want to first restrict to simple cycles. So I guess then it's not anymore necessarily infinite. And then the other thing, the very simplifying assumption is we do not consider the uncertainty in the estimated transformations, so the uncertainty in the essentials, for example, because the longer than the cycle would be, the more uncertainty you would accumulate, and after a certain number of edges, you would have pretty much lost any certainty in what you're going to expect. So what we do is we restrict ourselves first to cycles of length 3, so we check our triplets, and then we do we sample cycles that are used by spanning trees. So we generate a set of spanning trees in this graph, and then sample all the cycles that are generated by the spanning tree basis, and then we also only pick the shorter ones, so up to length 6, I think, in order to ignore for now the uncertainty accumulation.
Can you model the matching uncertainty and then plug it into this cycle estimation as you say, if you have a longer cycle, then obviously
you could, but the problem is the longer cycle is becoming less and less informative. So when you even, if I understand the question correctly, so if you walk along 100 transformations, even if you have just a little bit of noise on each of them, after accumulate 100 of those transformations, you are very unsure which position you should have or in which direction you should look. So there's anyway a spread out of uncertainty for longer cycles. Is that? Yeah. and going back to the example, so where the previous approach with the missing correspondences would of course not help because of this highly repetitive structure in the visual content. So we had this sort of result before, and this inference removes a lot of the false positive epipolar geometries, and the structural motion pipeline is able to recover this model, which looks like the right one. Okay, so this ends sort of the structured motion part. Now it comes to more the convex modeling part, and so since my talk is called structured motion meets convex optimization, so there is one work I did linking really both aspects. So I looked recently into some convex formulations for some subproblem in structured motion estimation. So when you know the orientation of the cameras already, then the estimation of the camera centers and the 3D points can be formulated as a convex problem, for example. People in the literature have proposed this, and they have reported quite long run times because they used very generic, for example, semi-definite solvers to address this. So after I gained some experience with first-order iterative methods for non-smooth convex problems, I just checked out how well it works for these kinds of problems, and it turns out that it works reasonably well, and it gives you also a very nice way to do some additional modeling that can be directly fed into the solver and doesn't need for example, reformulation of the problem as a second-order cone problem. So, but I'm not going really to talk much more about this. Just to mention, there is now one work that combines both worlds. So, I talked a lot about structured motion, which gives you essentially the camera poses and some sparse sets of 3D points. This is, for many applications, not enough. So, in particular, for example, cultural heritage preservation or visualization, you would like to have a dense model, which gained my interest in convex optimization, as explained in the next few slides. So let's say you want to do some 3D modeling, dense 3D modeling of a set of statues. So this was some other project. So the structure and motion pipeline gives you the camera poses and the set of sparse 3D points, which roughly corresponds to the geometry. How to convert this geometry into something that's a dense representation of the geometry. So we stayed for the moment with quite simple and fast methods to do stereo. So this is a depth map that you obtain by just doing some plane sweep correlation and local stereo, which looks, of course, very noisy. So you have somewhat relatively clear the statue in the middle, but of course the background is not modeled well enough. But you have lots of those images, so you have this kind of depth map for each of the input views. So when you do something like volumetric range image integration, which is a very simple and fast method, so the result looks something like this. So this, I think this is a somewhat modified version of VRIP, which is slightly more robust. The result, although it captures the geometry to some extent, it is not the kind of result you want to display or to visualize. So you have, for example, here lots of clutter, and of course here something is going on very wrong, which is also induced by the reflection on the base of the statue. So can we do better? Implicit representations are very nice because they allow you to, without further complications, model the 3D object of interest with arbitrary genus. So we stayed with this representation, meaning that each of the depth maps is converted to a clamped sign distance field. And now the question is, how do we combine those sign distance fields? And from some work I did with Tom Bock, it was then apparent that so something like L1 TV has very nice features because so the L1 TV or TVL1 model that gives you something like a geometric scale space. So by increasing the smoothness, what happens is not that the result you get is smoother, but actually smaller scale features disappear, which is exactly, so if you go again to this result, exactly all this clutter, which is very small scale, and also here. So if this is going to disappear, this would be a very good thing to have. So the model we formulated is, so on the smoothness side we use total variation, which essentially also translates to minimizing the surface area of the model you obtain finally. And for the data term, we wanted something robust in contrast to volumetric range integration, which has essentially a square data term. So we picked this L1-like data term, which really would give you, if you forget about the smoothness, the median of, so the per voxel median of the sign distance function you put in. The nice aspect of this is it's a convex program, although it's non-smooth. And in the original paper, we proposed this convex relaxation and alternating optimization procedure. In the meantime, I know it better. And so one implementation I use currently is based on augmented Lagrangian or equivalently on Douglas-Wakefield. So what are the results you get? So in this case it looks something like this. It is much nicer, although the small details are missing, and this is mostly because that at the time when we did it, so the resolution of the voxel space was somewhat limited by the available memory you have. Now I guess you can do much better models. So these are some other examples, so that showing that this approach is not only good for modeling isolated objects where you walk around like in a turntable sequence, but can be used to do also outdoor modeling, so some parts of cities and so on. Of course, here the problem that the voxel space is limited is a factor limiting or restricting the level of detail you're going to see. I also submitted my results to the Middlebury multi-view stereo evaluation, and I was very surprised that right out of the box we got very nice results, which are not too far away from very sophisticated methods like from Furukawa, but especially a slight reformulation of the problem that's more suitable for GPU implementation. So this is much faster than high quality approaches, and is almost in terms of speed on par as the approach by Paul Morel, so the UNC paper, which gives much inferior visual results. Okay. So, since I already started with looking at some convex optimization things, so and also how to accelerate those kind of procedures on the GPU. So I looked further into more general problems of labeling problems or segmentation problems. And one outcome or one result I'm going to explain here is, so I guess you know all the sort of standard graph cut formulation for doing binary segmentation, where we have a regional bias term here and some smoothness term based on the gradient there. People coming from continuous optimization, so first have proposed this model and here just the total variation term, and they have shown that even in the relaxed continuous setting you get back a perfectly binary result that's globally optimal. Then people looked at weighted total variation and got the same result. Then people looked at Riemannian metrics, and again the same holds. So after I learned a little bit about convex optimization, so I realized that probably the most general thing you can put here as a smoothness term is when the smoothness term, depending on the gradient, is a convex and a so-called positively non-homogeneous function. And then the minimizer of this convex relaxation is again something that's binary. So what can you do with this essentially, or what gives you this increased generality? So you can not only prefer certain locations where your segmentation boundary should go through, which would be, for example, weighted TV. You can also put a preference on the orientation. So what should be the local orientation in terms of the boundary normal when the segmentation boundary goes through a certain pixel or voxel. There's also another interesting relationship. So this function here having this properties is the support function of a particular convex set, which I know as wolf shape, and this convex set can be seen as an equivalent or extension of the capacity constraints you encounter in the graph cut formulation. So then this set would correspond to the capacity constraints in the corresponding maximum flow formulation. So yeah, special cases include, of course, the Chan-Wese binary segmentation problem, what you can do essentially with graph cuts, and also you can reformulate certain convex multi-labeling or certain multi-labeling problems as a convex problem, like with linear discontinuity costs, as shown by the construction of Ishikawa, and also Tom Bock has a great paper on that, looking at it from the continuous perspective. So just to here, shows you, so instead of, for example, isotropic capacity constraint, when this is the minimum cut, where the capacity is equal in all directions, so you can have something that's anisotropic. So depending on what's the local orientation of your minimum cut at this point, you have different costs.
Question?
Yes?
Have you seen that used like this, going away from or having some more Riemannian metric or some more Fitzler metric, some more interesting? Have that been used practically, or is that practically?
One answer might be this. I have no. So the one thing to do is when you look at this Ishikawa construction, for example, then The same reconstruction was proposed by Boykov in, I think, 98 already. So this corresponds to a labeling problem with a total variation smoothness term, which gives you naturally piecewise constant solutions. And when you look at stereo results, you clearly see in 3D so this piecewise constant behavior. The going to this more general sort of Finsler-like approach allows you at least to approximately model the surface more, the smoothness more as a smoothness on the 3D surface. So approximately something like minimizing the surface area for this multi-labeling problem, which gives you, in this case, so much smoother results when you have slanted surfaces. So this is one application. Some other application we looked into is medical imaging, where people have used something like flux terms to encode orientation preference, and we proposed and tried using this anisotropic capacity constraints to align the segmentation boundary with some preferred orientation, or in particular when you know in MR images, so the object of interest is darker than the surrounding tissue, that really you're not snapping into the reverse position, where because you might have a stronger edge there, but you really want to enforce that the segmentation boundary is there, where you have to transition from a darker, let's say, bone structure to a brighter tissue structure. So we have used that there as well. So recently also some interest of interest is extending this kind of modeling. So we have talked about just a holistic smoothness prior. So what happens if you, for example, have smoothness priors coming from multiple sources? In the simplest case, you have multiple orientations. All of them would be good, but you can only pick one of them. So how to combine those priors? And one obvious thing is to just look at the sum, which is again, of course, convex, and also is one homogeneous, one positively one homogeneous. So this is fine. There's nothing new here, and this capacity constraints actually turn out to be sort of the Minkowski sum of the individual capacity constraints. The other thing that's of non-problematic is the maximum. Then the capacity constraints turn out to be the convex hull of the union of the individual capacity constraints. But the most interesting case is the minimum. So let's say you have multiple orientation priors. So if your segmentation boundary coincides with one of the priors, there should be no cost. So the minimum is would be the good thing. But of course, this is not convex, so it's problematic. But there is something that goes in this direction of being the minimum, which was proposed in image processing. So then this is called infinite convolution, where you say you have the main signal, what you're interested in is U, and this decomposes in a series of other signals, and you apply the particular regularization on each of the individual signals, but the U has to be, you're really looking at this is the additive combination of the individual signals, and people have argued that this is in some sense a convex relaxation of the problem you cannot directly solve so easily, and it turns out that even that gives you a global optimal answer for binary segmentation problems. So this is, I have not written that down yet, so but it's some interesting fact nevertheless. So just to give an example for a very simple binary segmentation result. This is the typical image used in those papers, and we just want to binarize that image, so whatever looks rather is brighter should favor be white and what is darker should be black. So the smoothness you can add is like this corresponds to the graphical setting to look at the 4 neighborhood. So then you clearly prefer horizontal vertical edges, and the infinite convolution result looks like this, which is of course in the overall impression very similar, but there are some details that are different. So since there is not a big difference, I don't know if this model is too useful for just segmentation, but there might be an interesting connection to dictionary-based methods where this could make a difference and be very useful. But I haven't yet figured that out. This brings me already a little towards the I think more or less the final topic. So how am I doing in time?
I think about 5 minutes maximum.
Okay. So when you think about smoothness priors that were proposed, so in the plot them on some line, so you have 2 extremes. So you have the very parametric approaches like total variation or homogeneous regularization. The very other extreme would be, for example, conditional random fields. So recently there is some interest in a lot of interest in sparse representations, so in dictionary-based methods, which add, I think, a little bit of structure on top of what the CRFs do. There is something that's I think in principle very similar to sparse representation. That's the product of experts or field of experts model. But nevertheless, I think there is a gap, and I would like to look at smoothness priors that fall into this gap, so which are not as parametric as total variation and friends, but not as general as for example, sparse representations. Why is this of interest to me? So when it comes to 3D modeling, then stereo or depth map are play an important part. And in contrast to color images, depth maps do not show this rich structure in their statistics, but they show some structure which I think goes beyond parametric smoothness models. So these are just some depth maps for illustration. And the current model I tried. I'm not completely happy with it, but it's a first try. It's something that looks very much like sparsity. So the unknown U is the one you're really interested in. So you have, depending on your particular problem, so you have some data fidelity term, which might be some matching cost term or some approximation term. You say locally, when you look at U and take some local patch, this looks like it's generated by a number of elementary patterns you're going to expect. So this is the typical term you encounter in sparse representations, that a local patch of the unknown is generated by a dictionary, and the dictionary coefficients, there are also unknowns in the optimization problem. And then you have a prior on your dictionary coefficients, which in case of sparse representations is generally a sparseness prior, so they're one term. But we do not look at overcomplete dictionaries, but smaller dictionaries, so the prior here on the coefficients, there should be something different. This kind of model includes, of course, total variation regularization, and what we are interested in particular for modeling indoor environments is a piecewise planar model for depth maps, where the dictionary essentially consists of constant elements which compensate for the absolute depths, plus just linear gradients in vertically and horizontal direction to model the planar aspects, and this term here allows for piecewise planar models. So how does this look like? So for stereo, the results you get they look somewhat like this. So where you really see, especially the road, is a very nice example for something that has to be modeled in a piecewise planar way. So the road is perfectly, more or less perfectly planar. Yeah, you see occlusions because of this model. They show up usually as gradients in the depth map. That's some sort of property of the model. Since we're interested mostly or for this particular approach in modeling difficult indoor environments, so we apply this for indoor stereo, where we have lots of homogeneous walls, so no strong data term, and the total variation would give or favor piecewise constant solutions. So you would have sort of step edges in the result, and here this looks perfectly smooth. Since I'm here at the place where a lot has been done to make Kinect work, so although Kinect does not, so the raw depth map do not report depth values where you have specularities. So although the goal of having a plausible completion of the depth maps in difficult environments can be also done with this approach by just replacing the matching cost term by an approximation term. Okay, and this is, I think, pretty much the last slide. What I'm interested currently as well is back again to something like multi-view stereo. So I have presented some approach which first computes depth maps and then fuses them together. So there are approaches that do this simultaneously, like volumetric graph cuts, and there is in particular work by Karim Kolev from Daniel Kramer's group, which has some shortcomings because I do not believe the particular relaxation is very strong. And currently we are looking at other ways to directly compute a consistent 3D model from a set of images, which is exploiting or which is encoding so Mark's group is called the free space violation. So when you have multiple, for each camera you have one depth map, so you have multiple depth maps. So when do you see a conflict? So if one depth map tells you so the surface should be at this point, but the other one tells you this should be free space. So you have a conflict, and when you look at implicit representation of surfaces, this corresponds to a bilinear constraint, which you can relax to, in this case, essentially one linear inequality. And this is a student is implementing currently and making some experiments and some initial results for obtaining consistent symmetric stereo. You can see here, not too well, I guess. So here, this is the Teddy pair of images from Middlebury. So when you compute a global stereo result from left to right and right to left, so they do not match in particular. Here you have a region where it's inconsistent, and when you add this kind of constraints, you get a nicely consistent result. Yeah, I had lots of help in my work. So here are some faces from the Graz group. Here are some people from the UNC group, and these are some people I collaborate with at ETH. Thank you.